Okay, today we're going to talk about an overview of pressure transient analysis. I've had an epiphany and I'm redoing the notes in a way that makes more sense to you, maybe not to me. We're going to make one gigantic file, and by the end of the semester we'll have a perfect set of notes and you'll have contributed to it. You won't get anything out of it, of course, neither will I, but we're going to do it that way. We'll cut and paste pieces of it as we go along into the daily summaries so that you'll have that. What else, Dilhan? We laid out what we expect for the next week or so. That's in the, what do we call it, the daily summary file. It's number 5, so that'll be pretty cool. Mr. Little, you like homeworks, right? By the way, we've run out of blue paper soon, so we're going to start using yellow for quizzes. You like that? You know what else Dilhan told me this morning? You're not going to like this, but I sort of thought it was ingenious. They're going to grade the quizzes 0 and 100 as well. You think that's fair? Yeah, he said that you guys are so smart that you're all going to get hundreds anyway. That's actually not what he said. He's wondering now. How many of you remember the good, bad, and the ugly? Yeah, I looked at Dilhan a minute ago because he gave me some bad advice, and I called him Tuco, and he didn't like that very much. Somebody explain who Tuco was. He was the ugly Dilhan. Okay. So now we're going to start talking about how one actually performs a pressure transient test. And what I want to make sure of is that everybody understands that if you do not use bottom hole shut-in in a pressure buildup test, you better know, or you better estimate within a very reasonable accuracy how long wellbore storage is going to last. How many of you pay income tax? Anyone? No? What is your least favorite day of the year? April 15th. That's mine, okay? But lately I've been filing an extension, but you got to pay your taxes on April 15th, even if you file the extension to the 15th of October, whatever it is. Well, how do you get away from paying taxes? Anybody? Operate only in cash. That's a great idea if you're a crack dealer. Okay. Now, in the United States, our tax rate is what, 36% maximum tax rate? But then again, you pay sales tax and you pay some other things that basically qualify as tax. So we're probably in the mid-40s on every dollar you make. You have to pay that much back some way, somehow. And I know you're all thinking, well, not if it's, if I take only cash. But let's forget that for a minute. So approximately when is your tax freedom day when you pay taxes? Does anybody know? Plus or minus, that's a reasonable estimate. Okay, so somewhere around the end of May, the middle of May, depending on who's in office, the Republicans or so forth. Yeah, do you see the Republicans' objection to the bailout bill? Is that illegal immigrants cannot be allowed to get tax vouchers back on money they've already spent in. This is crazy. At any rate, you don't understand, but well, yeah, I'm a devout liberal. I think the United States is big enough to hold 6 billion people if they want to come in here. You don't like that, do you? Mr. Stone, you're thinking, good thing I got tenure, right? I'm going to taste real good. I saw a movie last night you'd like. It was called Doomsday. They cooked people and ate them, Yeah. It's kind of after the apocalypse, that kind of thing, yeah. So that tax freedom day, is that a good day for you guys? You don't even think about it because you're students. But wellbore storage behaves exactly the same way. You cannot get away from wellbore storage. And if you're looking at this diagram, you have to be thinking, what the hell is he talking about? Well, it's the part of the wellbore that stores fluid. So in this diagram, the part of the wellbore that stores fluid is around, it's this bottom part of the casing, around here, and all the way up to the top of the well, okay? So if you've got 2 miles of tubing, someone guesstimate the volume that 2 miles of tubing might be. Oh, we got somebody going to calculate it. Okay, let's do 2 inches divide by 24 squared. Are you trying to give yourself a tonsillectomy? Okay, you want to do it the hard way? So that's 2 inches. Divide by 12, I guess. We can do it that way, per foot. Okay? And then square that, right? And then multiply that by pi over 4. And then, well, let's divide that by what? 5.615 feet cubed per barrel. Give me a number. 0.003885. Did I do that right, Dylan? That's pi over 4 d squared. Eh? Yeah, I'm going to get there. That's barrels per foot, right? Okay. Is everybody okay with that? All right. Now multiply it. So that's going to be 2 times 5,280 feet times 0.00388. Is that right? Barrels per foot. How many barrels is that? How many? 41. How many of you remember the song Delta Dawn? 41, and her daddy still calls her baby. You got a problem with that? What happens when you have a daughter? You're going to freak out when the guy comes over to take her out, right? Nah, you're going to move to like somewhere in Canada. Okay, so that's 41 barrels. Is 41 barrels a lot or a little? Yes. Is that your answer, Mr. Stone? Anyone? Is that a lot or a little? What happens when now you multiply this by a relatively high compressibility fluid? Now the fluid has a lot of energy per unit volume, right? And that's going to make your life crazy. How can you minimize this 41 barrels? What happens, and I've covered it up here, my apologies, is you use a bottom hole shut-in valve and then you significantly reduce that volume. That volume is a penalty that you have to pay. You cannot put the measurement in the reservoir. You put it as close to the reservoir as possible. But the easiest way to explain wellbore storage is very simple. You have 2 systems. You have the wellbore and you have the reservoir. At first, the wellbore is going to dominate everything. When you begin producing, when you open the valve at the surface, where's the fluid coming from, Mr. Stone? The wellbore, not the reservoir. And then slowly the reservoir will kick in. If we were to draw a graphic of this, okay, so the surface rate is constant. All right? So the rate up here, Q surface, that's constant. But now what about the Q coming here? We call this Q sand face. What's the sand face rate going to look like? This is rate versus time. Okay? How's it going to increase? Man, I hate this pen. It's going to be very, very small. It's going to be 0. And then, like Guglielmo, it's going to get motivated, and then it's going to get up to a plateau. You like that, Guglielmo? Where are you at? He's not here. Oh, there he is. Okay? So here, QSF is approximately 0, right there. Here, QSF is approximately Q surface. Okay? Now this is a drawdown. Exactly the opposite happens when you shut the well in. Does that make sense? This is QSF drawdown in red, and then QSF buildup in blue. Now, when we shut the well in, what's the rate? The rate is 0. So Q surface buildup is 0. But what's the rate? The rate is still Q surface. Why? Because the wellbore is full of spongy fluid. Dilhan, are they going to have a quiz on this? You betcha. Okay. Now, how do you minimize this effect? How do you push it back this way? Anybody? Okay, but we can't do anything about the reservoir fluid. It's a good idea, but that's that. It is what it is in the vernacular of you homies, okay? So what else can we can minimize the volume. That's the only control variable we have. If it's high permeability, it'll come to equilibrium faster, by the way. If it's low permeability, it could take the equivalent of forever. What's forever, Mr. Stone? Months or years. Is that unbelievable? Yes, it is, but it happens. If the permeability is very low, what are you going to get? Dilhan, our friend who wanted more free consulting, called me today when we were in the office. They're looking at a 0.005 or so millidarcy formation. It's all wellbore storage, but he refuses to acknowledge this for reasons I'm not sure of. But that's okay. The lower the permeability, the more it's going to go this way. K down is going to go that way. Volume down, or volume of the wellbore down, is going to go that way. Why is this so important? I want you to be able to explain this to your mother. Why is this so important? Is everybody ready? I'm going to explain it to you. This is the wellbore. This is the reservoir. What's this? This is both. Okay? So if you're over here, you can analyze the wellbore. Anybody want to throw me a bone here? What good is it to analyze the wellbore? 0.0 good. Why? Because you know what's in the wellbore. Now you can calculate some things using the wellbore storage domination period, like you can calculate the initial pressure or the pressure at the start of the test, because there's some unique things about that. But Dylan, what else can we calculate? We can reverse calculate the volume of the wellbore, which is completely irrelevant. We don't need to know that. Okay? And what about this no man's land or no person's land? What can we do there, Mr. Sullins? Nothing. Okay? What can we do over here in the reservoir? Over here in the reservoir, we can calculate K, S, XF, ... Okay? So our goal as petroleum engineers is to evaluate the reservoir, and we're going to have to pull this thing over here. The only way we can do that physically is to constrict the wellbore. Interesting, huh? What's the most significant innovation that has occurred since this slide came out some 25 years ago? How many of you worked for the service sector? What'd you do? Painted pipe. Come on, hurry up. Okay, they isolate their zones, they perforate. Could you be a little more vague? Anybody? Anybody else? He's on the right track. Okay, about 15 years ago, a company in Canada came up with a one-shot device that was a perforation that had a pressure and temperature sensor on it, and you ran it on the outside of the casing, okay? This effectively gives you a measurement point at the reservoir forever. It's still affected by wellbore storage, but you can get pressure and temperature from that. Mr. Sullins, is it likely that you're going to clip the cable putting this in? Possibly. They claim 99% success. They claim 99% success. How many of you in here wanted to be electrical engineers and it didn't work out? Nobody. Okay. What do you know happens to electronics that are exposed to heat and pressure and corrosive fluids over time? Okay. Well, this was a different kind of device. It had no electronic parts. It was queried using the umbilical cable. There's nothing down there except the sensor. Now, I don't know how accurate it is, but based on how it was constructed, it was not supposed to degrade over time. Now, I can show you, as can Dilhan, a lot of gauges that have degraded over time, and the worst of them go off and come back on. You just throw that away. That's kind of like a bad relationship. You don't want that. Okay, now, what we can do now from our friends at Schlumberger et al. Is we can actually put a continuous strip here for temperature and pressure measurement. Now, the pressure part's not so clear to me, but the temperature part is. You can have continuous temperature and pressure measurement in the borehole. Is it going to be cheap? No, it's going to be extremely expensive. Where are you going to use it? In your $100 million wells? What can you do if you have temperature as a function of position? What's that going to tell you? It's going to tell you possibly what fluids are there, because some fluids are different temperatures than others, and they'll run a PLT to check, and then they'll take a correlation, if you want to call it that, off the PLT, and they'll guesstimate the behavior of the fluid as a function of time from that. This is called distributed temperature. You're going to see more and more of this, distributed pressure as well. All right, I think I've just about covered everything my little brain can think about here. Wellbore storage is bad, but it's a tax you're going to have to pay. The difference between having downhole shut-in and not having downhole shut-in is what, Dilhan? A factor of 10? At least. Onshore, it's probably a factor of 5. Offshore, it's probably a factor of 10. Now, if you have downhole shut-in, you get to formation much faster. I did a job last semester, last fall, another one of these freebie deals from one of the guys you grew up with. They spent $90 million of somebody else's money on a reservoir development kind of close to where you're from, okay? And they went and tested the reservoir down the horizontal section, and they did not use bottom hole shut-in. They did not use surface readout. So in order to save a few bucks, they completely obliterated their ability to analyze the reservoir behavior. Just FYI. The other thing they should have done is they should have tested the pilot hole, which was vertical, instead of drilling 1,000 meters out and then trying to figure out what was going on there. And how many well tests had they run in exploration wells prior to this? But somebody gave them $90 million to do this. So they now have a great water well out in the middle of nowhere. It does produce oil as well. There's an interesting little story behind it. I'm sure Marmina will like this, being from the region. Marmina, they had the horizontal part going like this, and then somebody went on vacation, and it went like that. That's not good, right? What do you think happened? As Guillermo would say, mucho agua, okay? How do you remedy this? Fill it with cement and drill in the opposite direction? That's probably about all you can do. Of course, now that you've spent your partner's $90 million, they just want to see you dead, basically. All right, so any other questions about how this is going to behave? Are you going to measure the sand phase flow rate? Is there any company out there that measures sand phase flow rate continuously? No way. Now you can measure sand phase flow rate with a PLT, a production logging tool. You can measure it with some other tools. Schlumberger swears by their optical fluid analyzer that you can get a surrogate rate or an analog rate from that. Is there anything else that you can do? Can you put a permanent monitoring facility down there? Yeah, you can. Weatherford will say one, Baker Hughes will say one, Schlumberger will say one. How much does it cost? $1 bazillion. Okay, so where are you going to put something like this? Who are our friends from Aramco here? Nobody? Okay. Are you aware of the maximum reservoir contact wells? Yeah? So they drilled these crow's foot wells and they split them apart. These are laterals. This is a good idea, right? Yeah? Okay, what's the bad idea? They've got flow control and pressure measurement in all of these. But what's wrong with it? The application got ahead of the theory. What happens if one of these laterals goes bad? What happens if you're trying to evaluate the reservoir between lateral 1, lateral 2, and lateral 3? Now, we've been doing this for 20 years, but this is the first time anybody ever fully instrumented one. And they gave a presentation a couple of times last summer explaining that they don't know how to evaluate reservoir properties from these kinds of wells. You can't even model it very well because you don't know what's between them. So this is one of those challenges that kind of like learning to swim and then being, thrown in the ocean with a brick tied to your foot. This is going to be one of those tough times. They're going to have to figure out how to evaluate the reservoir. Did these wells achieve what you wanted? They're like, no habla English. Come on. Did they all achieve the desired maximum rate? Not exactly. Okay? Because the reservoir quality changed. You were chasing the lower quality part of the reservoir. You expected 10,000 barrels a day in all of them, and you didn't quite get that. What I'm getting at is for those of you who are going to be around these complex wells, you need to start thinking about how you're going to evaluate the performance in them. Let's forget picking on Aramco for a second, and let's pick on somebody else. Let's talk about Southwest Energy. Anybody here going to work for them? How many wells a day are they drilling? About 20. I don't know right now, but contractually, a few months ago, it was about 20. They're going to complete each one of these wells with multiple hydraulic fractures, correct? The future of the company rides on this. How much does each additional fracture add to the profitability of this well? They don't know. I mean, you could make this analogy for the Barnett Shale, you could make it for the Fayetteville, you could make it for the Woodford, but this is one of those trick questions. You're not expected to know what's going on here, but as someone who's looking at this sort of from an academic standpoint or from a young person standpoint, what's your thought process? We need to be able to characterize the performance in these kinds of wells. Is something on fire? I mean, is somebody burning marijuana or something? I mean, it smells like a nice smoky wood fire. Luke, do you have something in your backpack you want to talk to us? Okay. I mean, I see a little smoke in the Brownian motion. It's right over you, Guillermo. Okay, so here's what I'm telling you. You've got a simple reservoir configuration, a well reservoir configuration that we're going to talk about in this class. When you start looking at very complex well systems, do you think these hydraulic fractures have volume? You bet. Do you think those multiple laterals have volume? You bet. So all of these are going to mess up your ability, or let me rephrase that in technical terms. They are going to complicate your efforts to characterize the reservoir. So my advice, think simple first, and then come back and try something complicated. How many horizontal wells are being drilled in shale right now in the U.S.? Wild guess. Hundreds. That's a good guess. It's in the hundreds. I don't know if it's 200, 500, but it's in the hundreds. How many of them are going to be tested? Why? It's expensive, the permeability is extremely low, and that complex configuration I just showed you, you're going to get nothing out of that for 10 years, except one big, massive linear flow sequence. And you may be saying, well, that tells me something. It does, but it doesn't tell you anything useful. We've got to figure out how to do that. Okay, let's move on. Sorry for all the noise. All right. How many of you want to work for Exxon? Nobody? Finally, a hand goes up. Is that a finger or a hand? Okay. Why do you want to work for Exxon?
They're the number one company for a reason.
Yeah? You might want to wait for the interview for that kind of talk, okay? I keep thinking that, I'm out of phase with you guys, but whenever I was your age, George Michael came out, not came out, and he had this song that if you're going to do it right. And Exxon has a habit of doing it right, even if it causes them loss in the short term. They're the company that's probably going to develop, 25, 30, 50 of these kind of wells, test the bejesus out of them to see what they can determine from them. And this paper by Vela and Barnum was an attempt to show that. So here's what we're looking at. Someone asked me beforehand, what's a DST? It's a drill stem test. I'm sorry if I didn't explain that. Drill stem test. What does it mean to have a drill stem test? Someone? That means we're going to use drill pipe. And we're going to produce the well up the drill pipe. Is that an ideal situation? Why? You're drilling, okay. You're going to take the same assembly that you've been using to drill the well, thick walled pipe. You're going to put a special sub on the bottom, hopefully with some expandable packers on it. You're going to drop it down to the zone of interest. You're going to inflate the packers. You're going to open a shiv and you're going to allow the well to flow through. You've got gauges in it. What's wrong with that? Wellbore storage is going to be a big part of it. What else? Sorry? Okay, you're warm, but you're thinking of it in another way. Are you usually going to use 4-inch diameter pipe to produce a zone? It depends. If it's a high productivity zone, then it may push fluid all the way to the surface. What are you going to have inside the drill pipe? You got to have something. It may be water, it may be mud, and you may calculate how much of this you need so that when you open the valve at the bottom, it doesn't flow into the reservoir, vice versa, right? You're going to design it for that. So let's look at this, and let's see what's being tested. Man, this is like a Cheech and Chong movie. What is on fire? Okay, the oil rate, we don't have green, so I'm going to use this. Why are these rates dashed? What does estimated rate mean? Anybody? What is estimated rate? Sorry? It means they don't know what it is. Okay, this is a drill stem test. If it does not flow to the surface, you can't measure it. You can try to reverse calculate it from the pressure profile at the bottom, but the column of fluid is moving up, and you're not sure exactly how far and how fast and everything else. So this is a difficult task to estimate the flow rate. Then gradually we assume it flows at the surface right here, and then of course they shut it in. Now, why did they do this twice? They did it once, they did it twice, and then this is called extended flow. Why did they do that? And then this is called extended shut-in, although it's not very long. Okay, louder.
Is that to measure the fluids away from the wellbore and in the reservoir?
Does everyone understand what Mr. Stone said? The first one is to try to get the mud off the gauge. That's the simplest answer. The second one, you're going to produce enough fluid to where you do it again. You're trying to measure the initial reservoir pressure, okay? So the first thing that you notice is the first pressures are far above the normal reservoir pressure. This is the normal reservoir pressure here. That's PI or P bar, however you want to think of it, okay? But these points are way above that. Why? Because the second you open this thing, it sees the pressure in the mud column, okay? Now, it produces that off, and you get a nice little drawdown right here. The pressure goes down, and then it comes back up because they shut it in. Okay, Marmina, you ready? And then they do it again, and the pressure goes down, and then they shut it in, and it comes all the way back up. You'll notice that both of these came back to the initial pressure. That's what they were checking for. That's what they're trying to estimate is the initial reservoir pressure. Okay? Now, here's the hard part. The pressure is bouncing around here, and the rate is unknown. Do you think you're going to be analyzing this flow data? The book says we should be able to analyze drawdown and build-up data the same way. Okay? Same theory, same this, same that. What's the problem with the drawdown? Anybody? You can't keep the rate constant. If you can't keep the rate constant and you don't know what the rate is, as you can see they're estimating it, then you may as well throw in the towel. But why are we drawing the reservoir down for several hours? What are we doing to it? Okay, we're cleaning out the well. That's a good point. Same thing. But more importantly, what are we doing? We're causing the pressure distribution that I described to move out in the reservoir, well beyond the wellbore. Depending on permeability, compressibility, that determines its diffusive speed, how quickly it moves away. If it's high permeability and high compressibility, it'll move fast. Sorry, high permeability and low compressibility, it'll move fast. The equation is further down, and we'll talk about it later on when we derive it. But you have to agitate the reservoir. You can't agitate the reservoir by leaving it sit still. You have to agitate it by testing it. So if I want to find out, what Marmina is capable of, I'm going to have him run 10 miles, and then I'm going to monitor him afterwards. Is it really important that I monitor him while he's running the 10 miles? In that case, probably so, because I might kill him, right? But the same thing happens in well testing. If you did not design the test correctly, you can kill the well. There's a case history of a couple of years ago, confidential and all that, but a buddy of mine says that his company discovered a new play, can't tell you where it is, all that sort of thing. Somebody decides they want to see what the maximum rate they can get out of it is. So, they keep producing, they hear this rumbling, You know, it's pieces of the reservoir going through the choke. You know, they're smashing against it. And so all of a sudden, the rate just dies off. Flare goes out, everything else. So they said, well, what have we done? So they dropped the camera down. What do you think the wellbore looked like down at the bottom? It collapsed. So somebody playing around, not really thinking about what they were doing, collapsed the wellbore. Do you know what the pressure gradient in this well was? It was over 1. It wasn't just overpressured, it was super overpressured. And by doing that, they caused enough of a pressure drop to collapse the casing, to crush the reservoir around it, and that's that. I mean, you can see things like that happening in practice, not very often because people are going to throw some design at it. So we're going to go on ahead and we're going to let the well produce, and then we're going to shut in the well. We usually call this TP, and that's not toilet paper, that's production time. And then the pressure goes back up. So Mr. Little, for all the marbles so far, you have a choice, okay? You have 3 choices for your favorite rate. Ready? A constant rate, a variable rate, or a 0 rate. Which one is going to be your favorite? Why is a 0 rate going to be his favorite? Because that removes the most critical variable from this discussion. When we shut the well in, the only thing we're doing is measuring the pressure. There will be some afterflow, some of that wellbore storage stuff, but that's all we're going to get. Now, this is much too short a test. I want to warn you, this is 6 a.m. on August the 4th. This is 6 p.m. on August the 4th, plus or minus. I guess it's more like a little bit later than that. Somebody tell me, it's probably 7 p.m. If you were to produce in 13 hours, if you were to reach the boundary of the reservoir, is that a good thing or a bad thing? Why? It's time to work on your resume, right? Yeah. Now, technically, you probably won't see that unless it's super high permeability. And even if you do see that, it's a bad sign no matter what. Okay? I've seen Darcy reservoirs produce, and you'll see the boundary in a few days, but nothing ever in 13 hours. That'd be a bad sign. Okay? Dilhan, we got time for one more slide. Are you ready for the quiz? They're going to need it for the quiz.